So originally what was going on with the city of Delphos, we had a aging trickling filter plant. The plant was finding itself in non-compliance with the EPA discharge limitations. We had two things going on. The one thing was we're a combined sewer system. We have somewhere between 60 and 65% combined sewers. And we also had significant industrial contributors. So what the city did is they started investigating different types of treatment. We actually, at that particular time, we looked at an oxidation ditch. We looked at some newer technology, with that being the membranes. The membrane was the technology of choice.
Well, coming from a traditional activated sludge plant, I've actually told people it was like going from the Flintstones to the Jetsons.
When you do get like a sludging issue with a membrane, or what we experienced is with the flat plate, you actually had to remove the cassette, and we would remove the individual plates, and then we would basically just spray them off and then reassemble. It was a huge task. Again, we had 52,000 membranes within the plant, so it just seemed like, you'd get everything up and operational, everything would be going fine. You'd get a localized dewatering issue, and then you would have to spend a lot of time and energy trying to remove those cassettes, take them out of their modules, clean them up, and then put them back in. The other thing that we did notice during the sludging events, when we'd pump the trains down and take a look at the cassettes, the style of membrane that we had little permeate tubes that would connect to each individual plate. And what you would find is a lot of, like, we call it roping or re-ragging. It was like fine hair and lint, and anything that is just small would capture on or any object that's in its flow.
We were contacted by the city to come in. They were having failed membranes, which was drastically reducing the capacity of their wastewater plant. Their design capacity is 3.83 million gallons a day. They were barely able to treat 1 million gallons a day, and their average day flow coming to the plant is around 1 million gallons a day. So they needed help right away to come in and bring their plant back up to treatment capacity, its original design capacity. The main reason of the plant capacity failure was the fouling of the membranes they had in place at the time. Of that, they have a combined sewer system, so when it rains, the plant gets inundated with stormwater, and Ohio EPA is mandating that those overflows be controlled or eliminated.
Over a period of time, what we found out that with doing that, you're not only contaminating your stream, but you're not treating the wastewater the way it needed to be done.
And the wastewater plant was getting inundated with wastewater and high strength from even washing systems at the time. That was causing the plant to fail, to go into zero DO, and for the biological treatment of the system, that was very dramatic in reducing what they needed to do to meet the effluent requirements. What we saw, I think, BOD-wise, strengths coming in could range from normal 200 milligrams per liter concentrations up to 300 or 400 milligrams per liter concentrations, and then at night even higher than that when they're cleaning their facilities. And that's when we were then hired to do an evaluation of the membrane system they had here. And in doing that evaluation, we found that they had tremendous fouling of membranes, number one, but number two, there were a lot of other area and concerns that needed improvements. Things like screening was a big issue here. The screens that were installed at the time were allowing solids to bypass the screen, causing some of the fouling issues. They had influent hydraulic issues where the flow was not getting evenly split between the 5 membrane systems they had at the time. And then they had hydraulic issues at the end too, where the flow could not leave the membrane trains adequately, then causing backup and overloading of the membranes. In addition to that, the high power costs they were spending at the time to treat at $400,000 a year just in the membrane system, we thought was outrageous and felt we could do a much better job and cutting that cost down. So what we did then, in looking at membrane replacement, we got how they felt reliability in the membranes, how they could handle stormwater fluctuations and wastewater strength, cleaning capability, and all these manufacturers were then graded on those points. And when we saw this hybrid Fibracast membrane that was a combination of flat plate and hollow fiber all made into one membrane, that was a flexible membrane that could be cleaned, we felt that to be a big plus. I did a rating, and that's how we came up with Fibracast at the time being the top rated membrane manufacturer. Because the city had spent $32 to $34 million to build the original plant. Plant failed right at the beginning, within the first year. And knowing that we would have to spend millions of dollars to fix it, we wanted to look at ways to save money so that it could pay back the loans needed to fix the improvements needed at the plant. And one of the easier factors to do that with was the power cost. So we were looking at, when it was all said and done, saving $300,000 a year on power, which would then be used to pay the loan to fix the wastewater plant as needed. So,
with the addition of the changing of the technology with the membrane and the process and the screening and be able to reduce equipment, there's going to be a substantial amount of space left in this room. Less equipment means less power.
When we switched over to the different type of membranes, or the current membranes that we have now, again, it requires air, but with the tankage being smaller and the membranes being in a smaller area, there's a significant drop in the air consumption. The performance of the process was pretty inefficient compared to putting in a new membrane, which is designed more around efficiency. The effluent quality of the membrane technology is unsurpassed. They actually done, I think it was the USGS done a study here. You're removing like 98, 99% of all viruses and bacteria.
like the old membrane system had 52,000 plates. We're down to 16,000 membrane sheets from Fibracast. The original system they had 5 trains and then 2 permeate pumps per train, so a total of 10 pumps down there. They had separate blower or multitude of blowers, but down in the piping gallery, we'll be eliminating all those 10 permeate pumps and going with 3 permeate pumps plus 1 backup, which is utilizing the space much more efficiently. All the piping that's done down at the far end where all the biological tanks will be, that'll all be gone. So really, we only need about 1/4 the space. I would call this the membrane of the future.
We pump it from the lift stations via Fairbanks Morris pumps. It comes through, it goes into our headworks plant over here. From there, it went through a 3mm perforated screen, a step screen. From the post screening, it goes through a Schreiber grit and grease process. From that anionic tank, there is a submerged flight mixer in there. And then it would pump forward into what we call the pre-aeration tank. Inside that pre-aeration tank, we had a submerged mixer again, and then we also had some fine air diffusers. The concept there was we were looking for a biological nutrient removal. From there, it would free flow into the MBRs, and then it'd either be permeated out, wasted, or recirculated.
about the service, in most situations or most places, you normally have design and then you go on to installation and commissioning, and that marks the end of the project. Well, that's not the case for us. For us, we believe commissioning marks the beginning of a project. It depends upon how you bring in your engineering and service expertise, how you form a bond with the client, use their knowledge because it is their plant. They know their plant the best, and they help you as you help them.
You got to have the availability to look at your as rates. You need to know what your TMPs and your PSIs and your flux rates and permeabilities. You need to know what your airflow rates are and your RAS rates and the levels in the tanks. You need to have all that information. It just so happens that all the equipment out there is just pulled right here on easy to manipulate or an easy to maneuver around screen.
We here at Fibracast can operate the plant remotely. This is the real deal. This is what the operators at Delphos can see. So you have an aeration tank over here that pushes water or pushes the wastewater, the sludge, into the membranes. And you have your anoxic and your pre-aeration tanks that basically comprises the biological system. If you click on any trend, it shows you live data of what exactly is happening at Delphos. It'll show you when the operators have done a clean, whether it's a maintenance clean, a recovery clean. This screen would basically show you what your plant set points are. This will show you your train set points and maintenance clean schedule. Operators at Delphos can literally enable or disable when they want to do a clean, at what hour they want to do a clean, and it would happen automatically for them. Literally all we do is we do a bi-weekly report on how each train is operating, how much they've produced, what is the mode of operation. Through these screens you can actually see the TMP, the flow, the flux that is calculated depending upon the membrane surface area, and the permeability. It will also show you, these screens will also show you turbidity, the airflow rate that's going in through the membranes, the RAS rate, and several other parameters that are important for operators. Now, as you can see, we at Fibracast can remote into the system and we can operate it live for the operators. At the end of the day, it's the service with the engineering and the product that makes us not only the membranes of the future, but the company of the future.